So, hello everyone, sorry for this delay. So I think there's enough people in can get started. This is the final week of the lab, and we'll be talking about code optimization and the basic steps of how we can structure our code better and also make our models run faster. So some of the reasons why it's quite important to optimize your code. But, at this point in time, large-scale machine learning are becoming more and more increasingly. So, for example, even ChatGPT or those AI large-scale models, they would take hundreds of years to train under one CPU, so parallelization, and even when you manage 1 or 2% of performance, either if that's memory or CPU, that could mean like a huge amount of cost savings, and it's also better for the environment. And this scales even with very improvements in the performance. In contrary to acceleration, so buying more hardware, getting better computers, changing your code and structuring your code better, it leads to greater return. It doesn't have as much of a cost, and at the end, it scales better. So Intel is that even a 10 times gain in performance from AI accelerators, it can lead to cost savings of millions of dollars a month. So that could be Onyx, TVM, or any other framework that can boost the model speed. So some of the basic questions of how to write efficient code for machine learning purposes is how to do it in a manner such as that it will allow scalability and being able to keep track of, let's say, the code enough so you don't end up regressing the code accidentally. So the second is how can I track the performance of my code? So there are tools that can be used to track your time, memory, or like a pinpoint which of your program takes the most time to execute. And are there any kind of tools that can help more machine learning models even further? So let's say you have finished creating a model, you've done the feature engineering and all of it, and you're ready to deploy in production. There are tools that can altering the results that the model outputs its execution. So the first part of this lab will focus on efficient code design, so how to structure code in such a manner that it will allow you to cooperate with other people and have a clean base as, let's say, your initial point. The first way that can happen is by using descriptive variable names. So quite often developers are trying to save time, or they think using longer variable names is bad practice, but it actually, in some cases, it may be necessary in order to sustain the readability of the code. So, of course, a bit of let's say, attention should be paid, in which cases it should be used, but as a general rule, it's better to actually use descriptive names that show how your code operates. Another way you can have a clean code base is by adhering to the dry principle. So dry means don't repeat yourself. So every piece of code, let's say function or functionality within a system should only be implemented once and not exist in many different points within the same code base, as that can lead to let's say different bugs of like the same nature appearing at different points of the code. So you may fix one of them, but then you have to go through all of the other instances of the same operation. So it's very, very useful to structure your code in such a way so you don't write the same things again and again and again. And that can happen through many different ways. So that can be through abstraction or using other kinds of basic object-oriented principles. Another very important, this is, I think, one of the most important rules on this section, because it actually does affect the performance directly instead of being a side effect, of not having clean code. Removing unused variables and imports is very important, as if you do have unused variables and imports, they tend to, let's say, use more memory throughout execution of the program. The garbage collector, this depends on the programming language used as well, does not remove those variables from the memory, and it keeps filling up the memory without any significant reason. And especially in Python, something very important is when we're importing modules, make sure that you're actually using them or you're not importing more than you need, because even there's a simple import like TensorFlow is an example that comes to mind. When you import TensorFlow, there's a tangible delay when your code starts. So it checks for the GPU, makes other operations, but it significantly delays the start of your program. So if you don't need a module, so it's better to make sure and check that you have not imported it by mistake. In a more data science specific way, using alternative data frame implementations can boost the performance very much. So at this point, Pandas is the de facto data frame library for Python. Most people use it as it's their first choice, and that's what most of us first learned when we started out for data science in Python. But alternatives do exist, and they usually perform better in terms of speed, memory efficiency, or even in the manner they can operate. So they can, for example, you can run part of a query in one machine, another part in some other machine, so in a distributed manner. The first alternative is Polars. Polars is based on Rust. It has a very big focus on providing the best performance possible. So this is mostly in by using multi-processing and multi-threading when it executes every query it has to process. So it creates an execution plan and tries to filter and compose it in such a way that it's the most efficient as possible, and it does not run any kind of operations until the last possible moment. So that's lazy execution. That's called lazy execution, when you defer the execution of a specific operation. Let's say you want to sum data frame column. So that would happen at the end when you actually try and use the result for this Python library. A second alternative is Vix. Vix has a different focus, and that's on memory efficiency and being able to handle larger than memory datasets. So this is when a developer has to, for example, work on a huge dataset locally on his laptop or on his workstation, which may not be as big as a big server, let's say. They can use Vix, and it never puts the entire dataset inside the memory, so it's very, very efficient, and it scales quite well, especially for a large number of rows. Maybe for the number of columns, sometimes under specific cases may be more limited, but when you have a lot of rows, Vix is very useful and provides very good performance for the amount of resources it uses. The last alternative is modding. Modding is a bit different than the previous two alternatives. It's meant to more in the cases where you have, again, very big data sets and you want to run them let's say, the operations across many machines. So it focuses towards distributed operation. And this happens using libraries like Dask or Ray. And what's very interesting about this library is that the API it provides is directly compatible with Pandas. So let's say you have an entire project that uses Pandas for its data frame needs. You can just change the import in the top of the code, and everything else will just work. It's exactly the same API, and everything is meant to be compatible. Another way you can make your code more efficient is by using vectorized operations. That's when, let's say, Pandas and NumPy fall back to native C functions. So when you don't apply the same operation to every row of a column, you can use apply or iterate through it with a for loop, but that's not efficient. And just by restructuring your code to run in a vectorized manner, you can get a huge boost in speed. So an example that I ran for the purpose of this presentation is this. So in the first way, I ran it. I used a non-vectorized version which ran a Python function for apply, and that means it didn't fall back to a more optimized C version. So it was very slow. It took 20 seconds, but the vectorized version, which just used the native Pandas support for like dividing and multiplying in a very fast way, it took 0.01 seconds. So that's a huge boost just by changing a single line or 2-3 lines of code. So this may not always be the case, but there's a large amount of operations that Pandas does provide and that can be run in a more efficient manner, and you can find those in the documentation as well of Pandas. The last way, the last important way you are able to structure your code efficiently is by using parallelization. Let's say you have a function that's very simple, it runs very fast, but you run it many times sequentially. In this case, you can use parallelization and execute all the instances of that function at the same time. So for that, the multiprocessing module of Python can be used, or libraries such as task array that we discussed earlier as well. In this example, there's a function which just calculates the square of a few numbers, and we give it as an input a list with the variable we want to give to the f function, and as output we get a list with the same order of as the input we provided that has the output of the respective execution of that function. So for the second section of this lab, we will be discussing how to track machine learning code. The first way is by using a timer. So timer is already included in Python, and it's a built-in module. It provides the time since epoch. So you can first get that time before you execute something, then you execute the piece of code you are interested in profiling, and then you get again the time in seconds since epoch, and then by just subtract the difference you get for like the duration of the function, how long it ran. So this is a very simple way, but it can always it's easy to add for like to test something or to use as a quick alternative. Now there are more complex ways that would be using the memory profiler. So the memory profiler is found in the memory profiler package in PyPy. The only thing you need to use in order to track how much memory each line of your code is to add the profile decorator above the function you want to profile, and then you run your Python script or module through the memory profiler module itself. So you do not run your code normally, but you need to run it through the memory profiler module. The output of this tool is formatted in the way shown in the slide. It gives you a rundown of how much memory each line uses. So if you see a huge increase or decrease of memory when running specific lines, this means that it may be a potential part you may want to focus when trying to refactor your code or find the best places to refactor your code. A third way you can track your code performance is by using the line profiler. Again, the line profiler is can be found in PyPy. It's not provided by default in Python, but it's very easy to install. And in order to initialize it, you just need to create a line profiler wrapped function, and once you wrap that function, you can use it as you normally would, and then just print the stats using that profile object you have received when running the function. The output of the line profiler is has this format. So for every line of code it has analyzed, it gives you how much time spent, how many hits, so how many times that line was visited, and it gives you the runtime as a percentage, and I feel this is the most useful metric out of all here. So you can see again which parts of your code are underperforming in comparison with with the rest. So it's very useful to find potential bottlenecks. And the final, for the final section of the lab, we'll be talking about the Onyx and TVM framework and how they can be used to convert from, let's say, more common machine learning libraries. So that could be XGBoost, CatBoost, scikit-learn, to different representations. So each Onyx and TVM provides, let's say, the building blocks or some basic operations that you can use to translate a model from, for example, scikit-learn to that format, and then Onyx and TVM also provide their own execution engines. So those models, those converted models using that format can be used and run in way faster. And also, what's different about these libraries is that the execution providers that they can run in a lot of in the vast array of hardware and devices. So that would be within a browser, within a phone, or even like ARM or any kind of architecture. And the support to give is way larger than, for example, scikit-learn. You wouldn't be able to run a scikit-learn model within your device. So you can prototype your model on your desktop computer, but you can port it into different devices and it will run more efficiently as a bonus. So in this example, we see that a model converted using the Onyx format runs around 10 times faster, and it can be done with a few simple steps. So for this slide, we used the SKL to Onyx package. First, you need to provide it with an example input or the types of each column that you want to provide and the model itself. Then you write the model to at a local directory, and then you can load that model and run it as a normal, scikit-learn based model itself. So for this example, random forest classifier was converted, and the iris dataset that's provided with scikit-learn was used. The second framework we'll be talking about is TVM. Again, TVM is a very open format that can be used to convert models from one type, from one library to a more generic format. And again, it allows to run those models in a very, very optimal manner in many different kinds of hardware. So a TVM model can be converted using the Hummingbird ML package. So Onyx can be as well converted using that package, but I wanted to show examples of both. In this case, after we converted our model just by using single line of code, so this is very easy to do. We are able to get again like a significant amount of performance gain. So again, I think it was around 10 times faster. So at this part there was a demo plan, but due to the technical issues we had, I don't think they'll be able to actually access it, but I think we can move to the Q&A part of the session. So if anyone has any questions, feel free to type them in the chat. And okay, are there cases where TVM is better than Onyx, or is?
Read the question.
Yes, that's true. Yeah. Are there cases where TVM is better than Onyx, or is one strictly better than the other? So this depends from model to model. From our experimentation and our automation platform, we found out that it definitely varies from model to model. So I think personal observation is that logistic regression tends to perform better in Onyx, or like GPM, maybe better using TVM. But another factor that what's very important is the hardware that you are running your conversion on. So if you plan to run, let's say, your TVM model on a larger machine, you may get an even bigger boost if you actually do the conversion in a machine with similar hardware. So that's quite important as well. So both the model and the hardware matters. So there's no strict, let's say, manner in which the benefits are showing. So if Pandas alternative is faster, but we still use Pandas. So many of these libraries I mentioned, they don't yet have the adoption, let's say, that Pandas has. Polars, I think, is getting close, and it's very prominent, let's say. Pandas was the first library of, I think, such in that area, or like that had like all the operations, let's say, bundled together, and we still use it because that's what I think everybody learned. And in more complex scenarios, though, it's very common to use Ray, or even Dask, and perhaps also Spark-based solutions. So Spark is very big on this area. And should we use Number if our code cannot be vectorized? Yes. So again, we have to test whether it has a significant performance improvement, but it's good to use it anywhere you can. So get the biggest amount of, let's say, code running in C possible. So what methodology process do you use, or would you recommend for deciding which is better? So I feel this comes down to sheer experimentation and trying out the different kind of models in the hardware itself. So I can show you an example. And if you just give me a second of this. Let me check if I can Yeah. Yeah, so I cannot access an example from this network, but aside from that, to sum up, the answer to this question is you just have to try it out, and it's mostly on a case-by-case basis. So we are here at TurinTech trying to optimize as well and automate that entire selection process, and our model optimization is able to test those models under a variety of hardware and can get you the best cost efficiency and any metric you may wish to optimize. So, are there perhaps any other questions?
Okay, so if there are no more questions, we are going to end the webinar now. Thank you for attending the webinar today. Happy Valentine's Day, by the way. And if you have any follow-up questions, welcome to get in touch with our team via email.
And there's also a form, I think, on the TurinTech website you can use to contact us as well.
Yeah. Thank you. Thank you for your time. Enjoy the rest of the day. Bye-bye.